It was late February 2026 when the image file finished downloading onto the workstation at Goddard Space Flight Center. Another batch of spectroscopic data from Hubble. Another routine analysis of Comet 3, I-Atlas, as it continued its journey toward perihelion. The telescope had been tracking the interstellar visitor for months now, capturing its increasingly active behavior as it drew closer to the sun's warmth. The scientist reviewing the data that evening had done this same task dozens of times before. Download the files, run them through the automated processing pipeline, check for anomalies, generate the standard report. Most nights, nothing unusual appeared. Comets behave predictably once you understand their patterns. They heat up, they release gas, they brighten. The math works out, the models hold. But frame 4847 looked wrong. Not dramatically wrong. Not obviously corrupted or glitched. Just slightly off, in a way that made experienced eyes pause. The infrared signature wasn't matching the expected thermal profile. The comet's nucleus should have been cooling gradually, from dayside to nightside. A smooth temperature gradient dictated by solar heating and the rotation period. Instead, there was a hotspot, a very specific hotspot, roughly 400 meters below the surface, reading 47 degrees Celsius, warmer than it had any right to be. The first assumption was instrument error. Telescopes malfunction, sensors drift out of calibration, cosmic rays hit detectors and create false readings. The scientist flagged the frame, made a note in the log, and continued through the rest of the batch. 20 minutes later, frame 4903 showed the same anomaly. Same location, same temperature differential, same geometric precision. Now it was interesting. A quick search through the previous week's observations revealed the pattern had been there all along, just subtle enough that the automated systems hadn't flagged it as significant. The algorithms were looking for brightness changes, spectral anomalies, outgassing events. They weren't programmed to notice a localized heat source, maintaining constant output deep inside a frozen body that should be thermally inert at that depth. The scientist pulled up the comet's rotation data. 3 I-Atlas spins once every 6.8 hours. If this hotspot was real, if it was actually embedded in the nucleus, it should appear and disappear as the comet rotated, moving in and out of view. The scientist synchronized the timestamps with the rotation model and felt something cold settle in their chest. The hotspot appeared exactly when and where it should. It maintained its position relative to the nucleus. It pulsed with regularity, strengthening and weakening in a rhythm that didn't correspond to solar heating or any known thermal process. And most unsettling of all, it was getting stronger. Each observation showed slightly higher temperatures, slightly more organized structure. This wasn't instrument error. This was something inside the comet generating its own heat. Something that had been there since the first observations, quietly doing whatever it was doing 3.5 astronomical units from the sun, where everything should be frozen solid and dead. Within 48 hours, every major telescope with infrared capability was pointed at 3 I-Atlas. The initial observation wasn't a fluke. The thermal anomaly was real, and it was far stranger than anyone had imagined. The hotspot wasn't just a random warm area, it had structure. High-resolution thermal imaging revealed 7 distinct regions of elevated temperature, each one approximately 30 to 40 meters across, arranged in what could only be described as a helix pattern. They spiraled around a central axis deep within the comet's nucleus, descending from roughly 300 meters below the surface down to at least 500 meters. The temperatures were wrong for their location. At that depth, insulated by hundreds of meters of ice and rock, you'd expect some retained heat from the comet's formation, or perhaps from radioactive decay of trace elements. But the math didn't work. Natural radioactive heating would produce maybe 2 or 3 degrees of warmth. These regions were reading 40 to 50 degrees Celsius above ambient. Some pockets were even warmer, approaching 70 degrees. More disturbing was the symmetry. Nature rarely produces perfect patterns. Crystallization can create geometric structures, yes, but this was different. The 7 chambers, as scientists were now calling them, were evenly spaced. They maintained consistent distances from each other. They appeared to be connected by channels or filaments of slightly elevated temperature, creating a network that looked almost biological in its organization. Then there was the pulse. Every thermal imaging session captured it. The chambers would brighten, their temperatures rising by 5 to 8 degrees over the course of roughly 90 seconds, then gradually cooling back to baseline over the next 7 minutes. The cycle repeated with mechanical precision. Every 6.8 hours, synchronized with the comet's rotation, the entire system would pulse together, all 7 chambers heating simultaneously before returning to their resting state. Scientists tried to explain it with known physics. Maybe it was cryovolcanism, liquid pockets warmed by tidal flexing. But 3, I-Atlas, had no companion object to create tidal forces. Maybe it was chemical reactions, exotic ices decomposing and releasing energy. But the pattern was too organized, too regular. Chemical reactions tend toward chaos, not synchronization. Maybe it was pressure variations, gas pockets expanding and contracting as different parts of the nucleus faced the sun. But the timing didn't match. The pulses continued, even when those regions were in shadow, even when solar input should have been minimal. Whatever was generating this heat, it was operating independently of external conditions. It had its own rhythm, its own energy source, its own internal logic, and it was deep inside an object that had traveled between the stars for possibly billions of years, cold and dark and alone until now. The call went out at 3 in the morning Eastern Time on March 2nd, 2026. Not a formal announcement, not a press release, but a series of urgent phone calls to select members of the international astronomical community. The message was simple and terrifying in its implications. We need independent verification. We need it now. And we need absolute discretion until we know what we're looking at. Within 6 hours, observatories across 4 continents had reprioritized their schedules. The European Southern Observatory in Chile redirected the Very Large Telescope. The Keck Observatory in Hawaii cleared 2 nights of previously scheduled observations. The James Webb Space Telescope, already monitoring 3 I-Atlas as part of its Interstellar Object Survey program, increased its observation frequency from weekly to daily. A 48-hour communications blackout was imposed on all participating institutions. No social media posts about observations. No casual mentions at conferences. No preprint papers uploaded to archives. The astronomical community is usually transparent to the point of compulsiveness, sharing data and findings almost as soon as they're generated. This silence felt wrong, uncomfortable, but necessary. The reasoning was straightforward. If the thermal anomaly turned out to be an instrument artifact, a glitch in Hubble's infrared sensors, or a processing error in the data pipeline, then raising alarms prematurely would damage credibility and waste resources. But if the anomaly was real, if something genuinely unexplainable was happening inside 3I Atlas, then the world needed to hear about it from verified sources with overwhelming evidence, not from speculation and half-processed data leaked on social media. Those 48 hours felt eternal for everyone involved. Scientists checked and rechecked their calibrations. They pointed their instruments at reference objects with known thermal properties to ensure everything was working correctly. They ran simulations trying to reproduce the observed pattern using every conventional explanation they could imagine. Cryovolcanism models, chemical decomposition scenarios, fracture heating from structural stress, even exotic proposals involving magnetic field interactions or triboelectric charging. Nothing worked. Nothing came close. Every simulation produced either random noise or patterns that bore no resemblance to the organized pulsing structure inside the comet. The helical arrangement of chambers, the synchronized heating cycles, the precise geometric spacing, none of it could be explained by known physics, operating on a passive chunk of ice and rock. By the time the blackout period ended, 8 independent observatories had confirmed the findings. The data was consistent across different instruments, different observation methods, different analysis teams. The thermal anomaly was real, the pattern was real, and whatever was causing it wasn't on any textbook's list of natural cometary processes. The question nobody wanted to ask out loud was finally unavoidable. What if it wasn't natural at all? The raw infrared data was already remarkable, but it was just the beginning. What scientists needed was depth. They needed to see through hundreds of meters of ice and rock to understand what was creating those thermal signatures. Standard optical imaging was useless here. Light doesn't penetrate solid matter, but other wavelengths do, and with the right processing techniques, you can build a 3-dimensional map of a comet's interior. Enhancement Protocol Alpha was designed for exactly this purpose. Originally developed to study the internal structure of asteroids, the protocol combines multiple data sources into a single coherent picture. Radar observations provide density measurements. Infrared imaging shows thermal gradients. Spectroscopy reveals chemical composition. Computer algorithms stitch it all together, filtering out noise and enhancing genuine structural features. When the first enhanced images came back from the processing servers on March 7th, 2026, they revealed something that shouldn't exist. The 7 hotspots weren't just warm regions. They were chambers, genuine voids, or at least regions of significantly different density than the surrounding ice. Each chamber measured between 30 and 45 meters in diameter, with walls that appeared surprisingly smooth and regular. But it was their arrangement that stopped everyone cold. The chambers formed a helix, a spiral staircase descending into the comet's heart. They weren't randomly scattered. They weren't clustered in one region. They followed a mathematical curve, each chamber positioned precisely where it needed to be to maintain the helical geometry. The spacing between chambers was consistent, roughly 80 meters of vertical distance and 60 degrees of rotation around the central axis. The connecting structures were even stranger. Thin channels, perhaps 5 to 10 meters wide, linked each chamber to the next in the sequence. These weren't fractures or cracks. Fractures are chaotic, branching randomly as stress propagates through material. These channels were straight, purposeful, following the shortest path between chambers. Thermal imaging showed they were slightly warmer than the surrounding ice, suggesting some kind of heat transfer or fluid movement through them. At the base of the helix, roughly 520 meters below the comet's surface, the pattern terminated in what appeared to be a larger central structure. The resolution wasn't good enough to see fine details, but the shape was unmistakable. Spherical, approximately 70 meters across, connected to all 7 chamber chains through radial channels. Its temperature was the highest of all, reading nearly 85 degrees Celsius, hot enough to maintain liquid water if the pressure was right. This wasn't geology. Geological processes don't create helices. They don't build symmetric chambers connected by engineered-looking channels. They don't organize themselves around central hubs. Whatever had created this structure, it operated under principles that had nothing to do with random crystallization or thermal fracturing, or any natural process known to planetary science. The thermal pulsing was regular enough to set a clock by, but it took radar observations to reveal what was actually happening inside those chambers. The Arecibo Observatory had been decommissioned years ago, but the Goldstone Deep Space Network in California and the upgraded radar system at Greenbank in West Virginia were more than capable of penetrating a comet's interior. What they found added another layer of impossibility to an already inexplicable situation. The chambers weren't static. Their density changed rhythmically, expanding and contracting by measurable amounts. Every 90 seconds, the radar returns showed a decrease in density, as if the material inside the chambers was becoming less solid, more dispersed. Then, over the following 7 minutes, the density gradually increased back to baseline. The cycle repeated endlessly, perfectly synchronized across all 7 chambers. The frequency was 0.8 Hz, less than 1 cycle per second, a slow, steady rhythm that fell right in the range of what humans would recognize as a pulse or a heartbeat. Scientists are careful about anthropomorphizing natural phenomena, but the comparison was unavoidable. Something inside 3I Atlas was beating. Even more striking was the pattern's behavior over time. When scientists compared observations from early February to mid-March, they noticed a clear trend. The pulse was getting stronger. The density changes were becoming more pronounced. The temperature spikes were climbing higher. It was as if whatever process was driving this activity was ramping up, gaining energy, becoming more active as the comet approached the Sun. This acceleration didn't follow the normal pattern of cometary activity. Regular comets brighten gradually as they near the Sun because increasing solar radiation sublimates more ice from their surfaces. It's a smooth curve, predictable and well understood. But 3I Atlas's internal activity was increasing faster than solar input could explain. At its current distance of 2.7 astronomical units, it was receiving only about 14% of the sunlight that Earth gets. That shouldn't be enough to drive the dramatic changes being observed. The energy had to be coming from somewhere else. Either the comet had an internal heat source, something generating power independent of solar radiation, or it was storing energy accumulated over its long journey and releasing it now in response to some triggering condition. Either explanation raised profound questions about what comets could be, what they could carry, what might survive inside them, across the vast emptiness between stars. Scientists monitoring the observations began using a phrase that felt both accurate and deeply uncomfortable. The comet wasn't just heating up as it approached the sun, it was waking up. And whatever was inside those chambers, it was responding to stimuli, changing its behavior based on environmental conditions. That's not how rocks behave. That's how living things behave. Spectroscopy is how astronomers read the chemical composition of distant objects. Every element and molecule absorbs and emits light at specific wavelengths, creating a unique fingerprint. Point a spectrograph at a comet, and you can identify water, carbon dioxide, methane, ammonia, all the usual suspects. The technique is reliable, proven, and rarely produces surprises anymore. Until IATLAS decided to rewrite the rules. The first anomalous absorption line appeared in data collected on March 15th, 2026. A sharp dip in the spectrum at a wavelength that didn't correspond to any molecule in the standard database. At first, scientists assumed it was a blend of multiple known lines, creating an apparent feature at an unusual position. But when they tried to model it that way, nothing worked. The line was too narrow, too strong, and positioned exactly where nothing should be. Then came the second line, and the third. Within a week, spectroscopic observations had identified 11 distinct absorption features that matched no known substance. They weren't close to known molecules. They were completely novel. Whatever was producing these signatures, it was chemistry that hadn't been catalogued on Earth or anywhere else humans had looked. But the real shock came from the molecules that were identified. High-resolution spectroscopy of the gas streaming from IATLAS detected phospholipids, the fundamental building blocks of cell membranes. On Earth, every living cell is surrounded by a membrane made of phospholipid molecules arranged in a double layer. They're not unique to life. You can synthesize them in a laboratory, but they're strongly associated with biological processes because they're so good at creating boundaries between inside and outside, between a living system and its environment. The detection was confirmed by 3 independent observatories. The phospholipids were there, present in concentrations far higher than any prebiotic chemistry model predicted. They were being released from the comet's interior, presumably from the same region where the thermal and structural anomalies were located. Then came the chlorophyll analog. Not Earth's chlorophyll exactly, but something remarkably similar. A complex, organic molecule with a porphyrin ring structure surrounding a central metal atom. On Earth, chlorophyll uses magnesium. This molecule used nickel. The same nickel that had puzzled astronomers since IATLAS was first discovered, appearing in the comet's spectrum without its usual companion ion. The implications were staggering. Chlorophyll captures light energy and converts it to chemical energy. It's the foundation of photosynthesis, the process that powers most of Earth's biosphere. If something inside IATLAS was using a nickel-based version of the same molecule, it suggested a mechanism for energy harvesting. A way to capture whatever light penetrated the ice and use it to drive chemical reactions, to maintain those warm chambers, to power whatever processes were creating the rhythmic pulses. This wasn't just organic chemistry anymore. This was looking like biochemistry. The moment a scientist detects something that might be biological, the first instinct is doubt. Not cynicism, but healthy scientific skepticism. Every extraordinary claim requires extraordinary evidence, And nothing is more extraordinary than claiming to find life beyond Earth. So before anyone would even whisper the word biology in connection with 3I Atlas, the findings needed verification that went beyond reasonable doubt. 3 independent laboratories received identical raw spectroscopic data on March 21st, 2026. One in Germany, one in Japan, one in the United States. None of them knew what the others were analyzing. They used different software, different calibration methods, different reference databases. The goal was simple. If all 3 labs reached the same conclusions working independently, then the results were real. It took 4 days. On March the 25th, the reports came back. All 3 laboratories identified the same phospholipid signatures. All 3 detected the nickel-based chlorophyll analog. All 3 confirmed the presence of amino acids in the gas emissions. And crucially, all 3 noted the same detail that made contamination nearly impossible to explain. The amino acids showed left-handed chirality. This needs some explanation. Amino acids can exist in 2 mirror image forms, left-handed and right-handed, chemically identical, but spatially reversed like your left and right hands. In non-biological chemistry, you get equal mixtures of both forms, but Earth's life exclusively uses left-handed amino acids. It's one of biology's great mysteries, this preference for one form over the other, but it's consistent. Every living thing on Earth uses the same handedness. 3I Atlas's amino acids were also left-handed. Not all of them, but there was a clear preference. Roughly 70% left-handed versus 30% right-handed. That kind of imbalance doesn't happen in ordinary chemistry. It requires some selective process, something that favors one form over the other. On Earth, that selective process is life itself. The contamination protocols were triple-checked. Could these molecules be coming from Earth somehow, contaminating the observations? Spectroscopy doesn't work that way. You're analyzing light from an object hundreds of millions of kilometers away. There's no physical contact, no sample handling, no opportunity for terrestrial molecules to mix with cometary ones. The signatures were real. Could they be from Earth microbes that somehow got onto the comet? 3I Atlas has been in space for billions of years, traveling between star systems. No Earth organism could survive that journey, and no Earth mission has ever come close to intercepting an interstellar object. The conclusion was becoming unavoidable. The molecules were indigenous to the comet. They formed there, or they were carried there from wherever 3I Atlas originated. And their chemistry looked biological, because it probably was. Something inside that comet was alive, or had been alive, or was made by something that was alive. Energy doesn't appear from nowhere. It's the first law of thermodynamics, as fundamental to physics as gravity. Every process that generates heat, every chemical reaction, every living organism requires an energy source. For 3I Atlas, the energy budget wasn't adding up, and that was perhaps the strongest evidence yet that something extraordinary was happening inside. Scientists calculated the comet's energy inputs with precision. At 2.7 astronomical units from the Sun, 3I Atlas received approximately 140 watts per square meter of solar radiation. Given the comet's size and reflective properties, that translated to roughly 12 million watts of total solar energy absorbed. Most of that energy went into heating the surface and sublimating ice, processes that are well understood and easily modeled. But the internal chambers were generating their own heat that couldn't be explained by solar input alone. The 7 chambers, plus the central sphere, were collectively producing an estimated 8 million watts of thermal energy. That's 8 megawatts, roughly enough to power a small town. And it was coming from deep inside the comet, where sunlight barely penetrated, and temperatures should be near absolute zero. The numbers were checked and rechecked. Different teams used different methods. Infrared measurements gave one estimate. Radar observations provided another. Spectroscopic analysis of outgassing rates offered a third approach. All the methods agreed within acceptable margins of error. The comet was producing more energy internally than external heating could account for. Something was generating power down there. Radioactive decay was the first conventional explanation. Certain isotopes release heat as they break down, and this process powered Earth's interior for billions of years. But the required amount of radioactive material would be enormous, and spectroscopic observations showed no evidence of the daughter products that radioactive decay produces. No unusual uranium signatures, no thorium, no potassium-40. The chemistry was wrong for that explanation. Chemical reactions were another possibility. Maybe exotic ices were decomposing, releasing stored energy. But calculations showed that even highly energetic reactions couldn't sustain 8 megawatts continuously for the months that observations had been ongoing. You'd need an implausibly large reservoir of reactive materials, and they'd be depleted quickly at this rate of energy release. That left metabolic processes. On Earth, living things generate energy through metabolism, breaking down nutrients or capturing light energy and converting it to chemical forms that cells can use. Humans metabolize food. Plants metabolize sunlight. Bacteria at deep sea vents metabolize chemicals from volcanic emissions. All of them produce heat as a byproduct. If something inside 3I Atlas was metabolizing, using that nickel-based chlorophyll to capture whatever light reached it, or processing chemicals from the comet's interior, it could explain the sustained energy output. It would explain why the activity was increasing as the comet approached the sun and more light became available. It would explain the rhythmic pulses that looked so much like biological cycles. The energy budget was pointing toward the same conclusion as the chemistry. Life. Somehow, impossibly, 3I Atlas was carrying something alive. Once scientists knew what to look for, they went back through every observation of 3I Atlas since its discovery in 2025. Thousands of images, hundreds of spectroscopic readings, radar data from multiple observatories. The question was simple but haunting. Had the signs been there all along, missed because nobody was looking for them? The answer was yes. The thermal anomaly appeared in the very first infrared observations, taken in April 2025, when the comet was still 6.2 astronomical units from the Sun. Back then, the hotspots were faint, barely above the noise threshold of the instruments. The automated processing systems flagged them as potential artifacts and filtered them out. Standard procedure. Telescopes generate false signals all the time from cosmic rays, detector glitches, electronic interference. You filter aggressively or drown in noise. But the signals weren't random. When scientists plotted the thermal readings over time, they saw a clear progression. The chambers were there from the beginning, maintaining their helical arrangement, pulsing at the same 0.8 Hz frequency. They were just quieter, generating less heat, cycling with lower amplitude. As 3I Atlas moved closer to the Sun over the following months, the activity steadily increased. The temperature differences grew larger. The pulses became more pronounced. The energy output climbed. It was a perfect correlation with solar distance. The closer the comet got to the Sun, the more active whatever was inside became. And the relationship wasn't linear, it was exponential. Small increases in sunlight triggered large increases in activity. Exactly what you'd expect if something was photosynthesizing, capturing light energy and using it to drive internal processes. Early spectroscopic data told the same story. The phospholipid signatures were present in observations from June 2025, though at much lower concentrations. The nickel-based chlorophyll showed up in August data. The amino acid detections went back to September. Every biosignature that seemed shocking when discovered in March 2026 had been quietly present in the data for months, overlooked because they were faint and because nobody expected to find them. One particularly haunting detail emerged from the review. In July 2025, an undergraduate student working on data analysis had written a note in the observation log. Temperature readings show persistent warm spot at depth. Possible instrument calibration issue. Recommend follow-up. The follow-up never happened. The observation was filed away, forgotten in the flood of data that modern astronomy generates daily. The pattern had been there the entire time, written in infrared light and spectral lines, waiting for someone to notice. It took an accidental close look at frame 4,847 months later to finally see what 3I Atlas had been trying to show from the beginning. It wasn't hiding. Humans just weren't looking carefully enough. And now the question was, what else had been missed? What other signals from the cosmos were sitting in archives, filtered out as noise when they were actually the most important data ever collected? Life on Earth exists in places that seem impossible. Bacteria thrive in boiling hot springs where temperatures exceed 100 degrees Celsius. Microbes live in Antarctic ice, dormant for millions of years, reviving when conditions allow. Organisms cluster around deep-sea hydrothermal vents, where toxic chemicals pour from the ocean floor and sunlight never reaches. If life can survive in these extreme environments on Earth, why couldn't it survive inside a comet traveling between stars? The extremophile hypothesis offered the most conservative biological explanation for what was happening inside 3I Atlas. It didn't require alien biochemistry or unknown physics. It simply required life to be tougher, more adaptable, more persistent than most people assumed. And Earth's own extremophiles proved that life could be exactly that tough. Consider Deinococcus radiodurans, a bacterium that can survive radiation doses thousands of times higher than would kill a human. It lives in nuclear waste, in the cooling water of reactors, anywhere radiation is intense enough to shred DNA. The bacterium has multiple copies of its genome and sophisticated repair mechanisms that can reconstruct genetic material even after it's been blasted apart. If microbes like this exist on Earth, why not versions that could survive cosmic radiation during an interstellar journey? Tardigrades are even more impressive. These microscopic animals can survive being frozen to near absolute zero, heated to 150 degrees Celsius, exposed to vacuum, and blasted with radiation. They enter a state called cryptobiosis, where their metabolism drops to less than 0.01% of normal. In this state, they can survive for decades, possibly centuries. When conditions improve, they rehydrate and resume normal activity within hours. 3. I-Atlas could be carrying something similar. Microorganisms that entered dormancy when the comet was ejected from its birth system billions of years ago. They survived the long, cold journey through interstellar space by shutting down completely, preserved in ice, protected from radiation by hundreds of meters of rock and frozen volatiles. Then, as the comet approached our sun and warmth began penetrating its interior, they woke up. The thermal chambers could be colonies. The pulsing could be metabolic cycles ramping up after eons of dormancy. The phospholipids and amino acids could be waste products or structural materials being released as cells multiplied and rebuilt their populations. The nickel-based biochemistry might be an adaptation to the comet's particular chemical environment, using available elements to construct photosynthetic machinery. This hypothesis had the advantage of requiring no new physics. It extended known biology to an extreme environment rather than inventing entirely new forms of life. Scientists liked it because it was testable, falsifiable, grounded in observations of terrestrial organisms. But it also raised an uncomfortable question. If extremophile life could survive inside 3 I-Atlas during its journey from another star system, then comets might be carrying biology all across the galaxy. And if that was true, where did that life originally come from? Where was its first home? For over a century, panspermia has been one of science's most provocative ideas. The hypothesis suggests that life didn't originate independently on every planet where it exists. Instead, it spreads through space, carried on comets and asteroids and dust grains, seeding worlds across the galaxy. Most scientists treated it as interesting but unprovable speculation. 3. I-Atlas was turning speculation into testable reality. The concept isn't new. In the 1900s, scientists proposed that simple organisms, or at least organic molecules, could survive the journey between planets, shielded inside meteorites. When rocks are blasted off a planet's surface by asteroid impacts, some fragments escape into space. Martian meteorites have been found on Earth. Earth rocks have presumably reached Mars. If hardy microbes were embedded in those rocks, they might survive the transfer. But interplanetary panspermia is one thing. Interstellar panspermia is far more challenging. The distances are enormous. The journey times are measured in millions or billions of years. Cosmic radiation is relentless. Temperatures hover just above absolute zero. For life to survive an interstellar crossing, it would need protection beyond anything required for a trip between neighboring planets. 3. I-Atlas provided that protection. Hundreds of meters of ice and rock shielding whatever lived inside from radiation. Cold temperatures that would keep organisms in suspended animation, their metabolism shut down, their cellular machinery preserved, and time, billions of years potentially, for the comet to drift from its birth system to ours. If the extremophile hypothesis was correct, if something was alive inside that comet, then it had accomplished exactly what panspermia required. It had survived an interstellar journey. The implications were staggering. If life could spread this way, then the galaxy might be thoroughly contaminated with biology. Millions of comets ejected from every planetary system, each one a potential ark carrying dormant organisms. Most would drift in the void forever, never encountering another star. But some would, by pure chance, fall into new solar systems. And if conditions were right, if they impacted a world with liquid water and energy sources, the organisms they carried could revive and establish themselves. Earth itself might be a beneficiary. The late heavy bombardment 4 billion years ago pelted our planet with countless comets and asteroids. What if some of those impactors carried microbes from other systems? What if Earth's first life didn't originate here, but arrived from elsewhere, seeded by an ancient comet much like 3I Atlas? The chemistry supports this idea. The phospholipids, the amino acids with left-handed chirality, the energy metabolism, they're similar to Earth biochemistry, but not identical. Different enough to suggest independent origin, similar enough to suggest common ancestry deep in the galaxy's past. 3I Atlas might not just be evidence that life exists elsewhere. It might be evidence that all life, including ours, shares a common interstellar heritage, that we're all descendants of ancient organisms that learned to survive the crossing between stars. The thick disk origin changes everything. If 3I Atlas truly came from that ancient stellar population, as its trajectory suggests, then the life inside it could be 7 billion years old or more. That's older than Earth, older than our Sun, older than anything in our solar system. It would be life from an earlier epoch of the galaxy, when stars and planets formed under very different conditions. 7 billion years ago, the universe was younger, the galaxy was still taking shape, and the mix of elements was different. The first generation of stars contained almost pure hydrogen and helium. When those stars exploded as supernovas, they scattered heavier elements into space. The second generation of stars incorporated those elements, lived their lives, and exploded in turn, enriching the interstellar medium further. Each generation added more carbon, oxygen, nitrogen, iron, and all the other building blocks of planets and life. Thick disk stars formed during this intermediate period. They have lower metallicity than our Sun, meaning fewer heavy elements in their composition. The planets and comets that formed around those stars would reflect that chemistry. Less iron, less magnesium, less of the rocky materials that dominate Earth-type worlds, but plenty of volatiles, plenty of carbon and nitrogen and oxygen locked into ices and organic molecules. This explains 3I Atlas's strange chemistry. The nickel appearing without iron makes sense if the parent system simply had less iron to begin with. The carbon dioxide dominance fits a low metallicity environment where carbon is abundant, but heavier elements are scarce. The nickel-based chlorophyll isn't exotic, it's adaptive, using the most available metal for photosynthesis when iron and magnesium are in short supply. But if life emerged in that ancient system, it would have had billions of years to evolve before 3I Atlas was ejected into interstellar space. Earth's life went from single cells to complex multicellular organisms in less than 4 billion years. A biosphere with 7 billion years of evolutionary time could develop in directions we can barely imagine. Not necessarily intelligence or technology. Evolution doesn't inevitably lead to complexity, but potentially metabolic sophistries and survival strategies far beyond anything Earth's organisms achieved. The life inside 3I Atlas might not be simple bacteria. It could be something that evolved for billions of years in a comet environment, adapting to cold, to darkness, to long periods of dormancy, punctuated by brief episodes of activity when the comet passed near a star. It might have optimized itself for exactly this kind of existence. spreading through the galaxy one stellar encounter at a time, reviving whenever conditions allowed, dormant for the vast stretches in between. We might not be looking at primitive life. We might be looking at ancient life, perfected life, a survivor from the galaxy's deep past, carrying biochemistry and survival strategies that predate our entire solar system. And if that's true, then 3I Atlas isn't just a biological curiosity. It's a time machine, a living fossil from an era when the universe was fundamentally different than it is today. Not everyone was convinced. Despite the mounting evidence, despite the thermal anomalies and the biosignatures and the energy budget that didn't balance, a significant portion of the scientific community remained skeptical. And their skepticism wasn't rooted in stubbornness or denial. It was rooted in the same careful thinking that made the discoveries possible in the first place. Extraordinary claims require extraordinary proof, and claiming to find life beyond Earth was about as extraordinary as claims get. The primary counter-argument focused on chemistry, not biology. Complex organic molecules can form through purely abiotic processes without any involvement of living systems. Amino acids have been found in meteorites that clearly never hosted life. Phospholipids can self-assemble under certain conditions without cellular machinery guiding them. The nickel-based chlorophyll analog might be a natural catalyst formed through thermal processing of organic rich ice. None of these molecules individually proved biology. They were suggestive, yes, but not definitive. The thermal chambers could be explained through exotic ice physics. Perhaps 3I Atlas contained clathrates, cage-like structures where gas molecules are trapped inside ice lattices. When heated, these clathrates can release their trapped gases suddenly, creating pockets of warmth and pressure. The regular spacing might result from crystallographic constraints, patterns that emerge naturally when materials freeze and fracture under specific conditions. Nature produces geometric patterns all the time without biological intervention. Snowflakes are hexagonal. Basalt columns are hexagonal. Geometry doesn't imply life. The pulsing rhythm at 0.8 Hz troubled even the skeptics, but they proposed mechanisms. Resonant heating from the comet's rotation could create feedback loops where warming leads to gas release, which leads to more warming in a cyclical pattern. Chemical oscillators exist in non-living systems, reactions that cycle between different states with clock-like regularity. The Belousov-Jabotinsky reaction creates pulsing patterns in a beaker without any biology involved. Maybe 3I Atlas was hosting a massive, naturally occurring oscillating chemical reaction. The energy budget excess could be measurement error. Thermal modeling of comets is difficult. They're not uniform spheres with known thermal properties. They're irregular chunks of ice and rock with complex topography and unknown internal structure. Small errors in estimating surface area, or albedo, or thermal conductivity could throw off energy calculations by factors of 2 or more. Maybe the comet wasn't generating excess heat. Maybe scientists were just underestimating how much solar energy it was capturing. These weren't bad arguments. They were scientifically sound alternatives that deserved consideration. The problem was that each skeptical explanation worked individually, but taken together, they required an unlikely stack of coincidences. Exotic chemistry that mimicked phospholipids, clathrates arranged in helical geometry, chemical oscillators pulsing at biological frequencies, and measurement errors that happened to make it all look like life. Possible, Yes. But was it more likely than the simpler explanation that something genuinely biological was involved? There was another explanation that few scientists wanted to discuss publicly, but many thought about privately. What if 3I Atlas wasn't just carrying life? What if it was designed to carry life? What if the entire structure, the helical chambers, the thermal regulation, the perfectly timed pulses, wasn't evolved biology, but engineered technology? The idea seemed like science fiction, but the geometry kept nagging at researchers. Nature produces patterns, yes, but the 7-chambered helix was almost too perfect. The spacing was exact. The connections were purposeful. The central sphere at the base looked like a hub, a coordination point. This wasn't the messy complexity of evolved systems. It had the clean efficiency of something built according to a plan. If an advanced civilization wanted to spread life across the galaxy, how would they do it? You couldn't send living organisms exposed on a spacecraft. The journey between stars takes millions of years. No conventional life support system could function that long. But if you embedded organisms deep inside a comet, gave them everything they needed to survive in dormancy, and designed the structure to wake them up when approaching a star, you'd create something exactly like what was being observed. The nickel-based biochemistry might not be adaptation. It might be optimization, an engineered photosynthetic system designed to work efficiently with whatever elements the comet contained. The phospholipid membranes might be manufactured rather than evolved, created by molecular machinery to protect and organize the biological payload. The pulsing rhythm might be a monitoring system, a beacon indicating that the cargo was intact and functional. This hypothesis explained why everything looked so organized. It explained the energy efficiency and the precise geometry, and the fact that systems seemed to be waking up on schedule as solar input increased. These weren't the random products of evolution. They were features, built-in capabilities, designed by beings who understood biology and engineering, and who wanted their creation to survive the journey between stars. But it raised terrifying questions. Who built it? When? Where? And most critically, why? Was 3I Atlas a deliberate seeding mission sent to colonize suitable planets with life from an alien biosphere? Was it a Noah's Ark preserving species from a dying world? Was it an experiment, a probe designed to test whether life could survive and spread via cometary transfer? The artifact hypothesis had no more proof than the natural biology hypothesis. The geometry could be coincidental. The efficiency could be evolutionary optimization rather than intelligent design. But the possibility hung in the air during every conference call and every data review session. Scientists looking at those perfect helical chambers couldn't completely shake the feeling that they were looking at something built rather than something born, created with purpose by minds that understood exactly what they were doing when they sent 3I Atlas on its billion-year journey across the galaxy. As news of the findings began circulating through the scientific community in early April 2026, a more mundane but potentially devastating criticism emerged. What if the entire discovery was an artifact of data processing errors? What if the biosignatures, the thermal chambers, the pulsing rhythms were all illusions created by flawed analysis techniques or contaminated datasets? The concern wasn't frivolous. Modern astronomy generates such massive amounts of data that no human can examine it all directly. Automated pipelines process the raw information, applying corrections for instrument quirks, removing noise, enhancing signals. Each step involves assumptions and algorithms can have bugs. A single error in the processing code could propagate through thousands of observations, creating false patterns that look real because they appear consistently. Telescope pointing was another vulnerability. If Hubble's guidance system had a subtle drift during 3 I-Atlas observations, if the telescope was actually looking at slightly different positions than intended, then multiple observations might be sampling different parts of the comet. What appeared to be a pulsing hotspot might just be the telescope's field of view drifting across a static thermal gradient. The pattern would look rhythmic because the drift was regular, but it wouldn't reflect any real change in the comet itself. Software version mismatches offered another explanation. Different observatories use different data reduction software. If one observatory's software had a bug that enhanced certain spectral features, while another observatory's software suppressed them, then comparing observations could create phantom molecules that don't actually exist. The phospholipids might be real in one dataset and artifacts in another. But if researchers combine the data without accounting for processing differences, they'd see consistent detections where none truly existed. Critics also questioned the statistical significance of the findings. With thousands of spectral lines in any given observation, some coincidental matches to biological molecules were inevitable. It's the multiple comparisons problem. If you measure enough things, some will show false positives purely by chance. Maybe the amino acids and phospholipids were just the few accidental matches in a sea of measurements that showed nothing unusual. Independent verification was supposed to address these concerns. 3 separate laboratories analyzing the same data should catch processing errors. But what if all 3 labs used similar software based on the same underlying code libraries? What if they all made the same systematic mistakes? Truly independent verification required not just different teams, but different instruments, different observation methods, different analysis approaches. By mid-April, the criticism had reached a level that couldn't be ignored. Science progresses through skepticism and verification, and the stakes were too high to accept any findings without absolute certainty. If data contamination could explain even a fraction of the observations, then the entire biological interpretation collapsed. The scientific community needed proof that transcended any possible instrumental or processing artifact. They needed direct, unambiguous evidence that could only come from one source. They needed to send a probe to 3 I-Atlas and see what was inside with their own instruments. 3 I-Atlas was on a schedule that no amount of debate or verification could change. The comet was approaching perihelion, its closest point to the Sun, and after reaching that milestone, it would begin its outbound journey. Within months, it would be too distant for detailed observations. Within years, it would fade from view entirely, disappearing back into the interstellar void from which it came. If humanity wanted answers, the window was closing fast. On April 15th, 2026, the comet crossed inside 2 astronomical units, closer to the Sun than Mars. Its activity was increasing dramatically. Water production had jumped to over 200 kilograms per second. The coma, the cloud of gas surrounding the nucleus, had expanded to nearly 50,000 kilometers across. Invisible light, 3 I-Atlas was now bright enough to see with binoculars from dark sky locations, a fuzzy green smudge moving slowly against the background stars. The internal chambers were responding to the increased solar radiation, exactly as predicted by the biological hypothesis. Their temperature had climbed to nearly 90 degrees Celsius. The pulsing frequency had increased to 1.2 Hz, faster than before, but still maintaining its rhythmic precision. Spectroscopic observations showed the phospholipid concentrations had tripled. The amino acid signatures were stronger. New emission lines kept appearing as whatever was inside became more active. Scientists calculated that perihelion would occur on June 28th, 73 days away. At that point, 3I Atlas would be 1.4 astronomical units from the Sun, closer than Mars, receiving roughly half the sunlight that Earth gets. If the trend continued, the internal chambers would be approaching 120 degrees Celsius by then, hot enough to maintain liquid water under pressure. If something was alive inside, perihelion would represent its peak activity, the moment when the most energy was available, and biological processes could run at maximum intensity. But perihelion was also the beginning of the end. After that date, the comet would start receding, solar input would decrease, the chambers would cool, activity would decline. Within 6 months, 3I Atlas would be back beyond 3 astronomical units, dormant again or dying as its heat source faded. Within a year, it would be too faint for most telescopes to track. Within 2 years, it would be gone, racing out of the solar system at over 30 kilometers per second, never to return. 73 days. That was how long humanity had to decide whether to simply watch this cosmic mystery fade away, or to do something unprecedented. To send a spacecraft on an intercept trajectory, to land on an interstellar comet moving faster than anything humans had ever tried to rendezvous with, to drill through hundreds of meters of ice and rock, and to see firsthand what was generating those impossible thermal signatures. 73 days to launch a mission that would normally take years to plan. It was absurd. It was impossible. And it was happening anyway. On April 20th, 2026, NASA and the European Space Agency held a joint emergency meeting that would have been unthinkable under normal circumstances. They proposed launching an intercept mission to 3I Atlas in 14 days. 14 days from concept to launch pad, a timeline so compressed it bordered on reckless. But the alternative was letting the most important scientific discovery in human history slip away without ever confirming what it actually was. The mission couldn't be built from scratch. There wasn't time. Instead, engineers identified a probe already under construction, originally intended for a Mars sample return mission scheduled for 2028. The spacecraft was nearly complete, sitting in a clean room at Kennedy Space Center, undergoing final testing. It had the right propulsion system, the right power supply, the right basic architecture. It could be repurposed if everything went perfectly. The modifications were extensive but achievable. The Mars landing system was stripped out and replaced with a Comet Intercept package, a thermal drill capable of penetrating ice, a sample collection mechanism, a suite of cameras and spectrometers designed for close-range analysis. The original scientific instruments were retained where possible and supplemented with new sensors built from off-the-shelf components. Nothing was elegant. Everything was functional. The trajectory planning was the real nightmare. 3I Atlas was moving at 62 kilometers per second relative to Earth. Catching it required not just reaching the right location in space, but matching that enormous velocity. The only way to achieve it was a gravitational assist maneuver around Venus, using the planet's gravity to accelerate the spacecraft while changing its direction. The launch window was brutal, just 18 hours wide. Miss it, and the next opportunity wouldn't come until 3I Atlas was already past perihelion and beginning its outbound journey. Fuel constraints meant the probe couldn't carry enough propellant for a soft landing. Instead, it would use a hybrid approach. Fire engines to match velocity as closely as possible, then use a harpoon system to anchor to the comet's surface during the final approach. Once secured, the thermal drill would activate, melting through ice while the probe's weight and the harpoon anchors kept it stable against the outgassing that made comet surfaces so treacherous. The mission timeline was tight. Launch on May 4th, Venus flyby on June 8th, arrival at 3I Atlas on June 27th, one day before perihelion. Drilling would take approximately 16 hours to reach the first thermal chamber at 400 meters depth. If everything worked, if the launch succeeded, if the Venus flyby was precise, if the intercept happened as planned, humanity would have direct confirmation of what existed inside the comet by June 28th. One day before 3I Atlas reached its closest approach to the Sun, and whatever was inside reached peak activity. One chance to witness something that had traveled across the galaxy, carrying secrets from another star, another time, perhaps another form of life entirely. One chance, and the clock was already running. The engineering challenges were staggering, and each one carried the potential to end the mission before it even started. Matching velocity with an object moving at 62 kilometers per second required precision beyond anything attempted before. The fastest spacecraft humans had ever built, the Parker Solar Probe, reached speeds of nearly 200 kilometers per second. But that was falling toward the Sun with gravity doing most of the work. Accelerating sideways to match a comet's trajectory while fighting against orbital mechanics was entirely different. The Venus flyby became the linchpin of the entire mission. The spacecraft would approach Venus from a specific angle, passing just 6,000 kilometers above the surface, closer than most satellites orbit Earth. Venus's gravity would bend the trajectory and add velocity, slingshotting the probe onto an intercept course with 3I Atlas. But the margin for error was microscopic. An approach error of just 10 kilometers would throw off the final trajectory by hundreds of thousands of kilometers. The probe would miss the comet entirely, sailing past while the world watched in failure. Then there was the ice-penetrating drill, a piece of equipment never tested under actual cometary conditions. On Earth, drilling through ice is straightforward. You apply downward pressure, the drill bit grinds through, friction generates heat that helps melt material. But in the microgravity environment of a comet's surface, there's no weight pressing down. The drill would have to pull itself into the ice using screw thread anchors, while simultaneously melting a path forward. If it encountered rock or dense material, it could jam. If it melted too quickly, liquid water might refreeze behind it and trap the drill bit. The thermal control systems added another layer of complexity. The drill would generate tremendous heat during operation, potentially hundreds of degrees Celsius at the cutting face. But it would be operating inside a comet where ambient temperatures hovered around -150 degrees Celsius. Managing that thermal gradient without cracking drill components or causing catastrophic failure required materials and engineering that had never been tested in these conditions. Power constraints limited everything. The probe carried solar panels and a small radioisotope power source, enough for perhaps 36 hours of intensive operations after arrival. That meant drilling, sampling, and analysis all had to happen within a day and a half. No second chances. No time for troubleshooting. If the drill jammed at 300 meters depth, there was no way to pull it back up and try again. Communication delays complicated operations further. Even at its closest, 3I Atlas would be light minutes away from Earth. Commands sent from mission control would take minutes to arrive. Telemetry from the spacecraft would take minutes to return. Real-time control was impossible. The probe would have to operate with significant autonomy, making decisions based on pre-programmed instructions and sensor feedback. If something unexpected happened, if the drill encountered conditions different from what models predicted, the onboard computer would have to adapt without waiting for human input. The entire mission rested on 14 days of frantic preparation, untested hardware, and the hope that nothing went catastrophically wrong. The secret couldn't hold. On April the 28th, 2026, 4 days before the scheduled launch, someone uploaded a 50-page document to a public file-sharing site. The document contained thermal imaging data from 3I Atlas, spectroscopic analysis showing biosignatures, and internal NASA communications discussing the emergency intercept mission. Within 30 minutes, the file had been downloaded 2,000 times. Within 2 hours, it was trending on every major social media platform. The leak was anonymous, but sophisticated. Whoever released the information had included enough technical detail to prove it was genuine, while formatting it in a way that made the implications clear, even to non-scientists. Highlighted sections pointed out the amino acids with left-handed chirality. Annotations explained why the thermal chambers couldn't be natural geological formations. A summary page laid out the case for biological activity in plain language that anyone could understand. Reddit's space communities erupted first. Discussion threads multiplied faster than moderators could track them. Some users dove deep into the technical data, debating spectroscopic calibration and thermal modeling assumptions. Others focused on the bigger picture. If the findings were real, if something was alive inside that comet, it meant humanity was no longer alone. It meant life existed elsewhere in the universe. It meant everything was about to change. Twitter amplified the story beyond the science community. Within 6 hours of the leak, hashtags related to 3I Atlas were trending globally. News organizations scrambled to verify the documents, reaching out to astronomers and NASA officials who suddenly found themselves unable to deny or confirm without violating their own institutional protocols. The silence from official channels only fueled speculation. By midnight Eastern Time, the story had jumped to mainstream news. Cable networks interrupted regular programming with breaking news banners. NASA discovers possible alien life in comet. The wording was carefully hedged, possible, and life in comet, rather than definitive claims. But the message was clear. 24 hours after the leak, 1 billion people knew that something extraordinary had been found in 3I Atlas, even if the details remained uncertain. Conspiracy theories emerged alongside legitimate analysis. Some claimed the leak was intentional, a controlled release to prepare the public for an official announcement. Others insisted it was disinformation, a hoax designed to distract from other issues or test public reaction. to potential alien contact scenarios. The most extreme voices declared that governments had known about extraterrestrial life for decades and were finally being forced to admit it. NASA's hand was forced. There was no point maintaining secrecy when the core findings were already public. On April the 29th, at 2 in the afternoon, the agency scheduled an emergency press conference for the following morning. 36 hours after the leak broke, the world would finally hear the official version of what scientists had found inside 3I Atlas and what they intended to do about it. The age of speculation was ending. The age of confirmation was about to begin. The auditorium at NASA headquarters was packed beyond capacity on April 30th, 2026. Journalists from every major news organization filled the seats. Camera crews lined the back wall. The overflow crowd watched from monitors in adjacent rooms. Everyone knew this would be historic. Nobody was certain exactly how historic until the presentation began. The opening statement was carefully constructed, each word chosen to convey scientific precision while acknowledging the extraordinary nature of the findings. Observations of Comet 3, I the Atlas, have revealed thermal and chemical signatures that are difficult to explain through conventional geological or chemical processes. Multiple independent teams have confirmed the presence of complex organic molecules, including phospholipids and amino acids showing preferential chirality. Internal structures exhibit geometric patterns and energy outputs inconsistent with known natural phenomena. While we emphasize that alternative explanations remain under investigation, the data is consistent with biological activity. Consistent with biological activity. That phrase, buried in the middle of technical language, was what the world heard. The qualifications and caveats disappeared in the translation from scientific caution to public understanding. Within minutes, news headlines around the globe proclaimed variations of the same message. NASA confirms alien life found in interstellar comet. The scientists had said possible and consistent with, but the public heard definitive confirmation. The presentation continued with data visualizations showing the helical chamber arrangement, spectroscopic graphs highlighting biosignature molecules, thermal maps revealing the pulsing energy patterns. Each image was compelling on its own. Together, they built a case that even skeptics found difficult to dismiss entirely. Something unprecedented was happening inside 3I Atlas. Whether it was life or some exotic chemistry that mimicked life's signatures, it demanded investigation. The announcement of the intercept mission landed like a bomb. A spacecraft would launch in 4 days on May 4th. It would reach 3I Atlas on June 27th, 1 day before perihelion. It would drill into the comet's interior and directly sample the thermal chambers. Humanity would have definitive answers within 2 months. The compressed timeline shocked even the journalists familiar with space operations. Missions normally took years to plan. This one had been designed in weeks. Questions came rapidly after the formal presentation ended. How confident are you this is actually life? What are the implications if confirmed? Could this represent a threat to Earth? Is there any possibility of communication? The answers remained cautious, emphasizing uncertainty and the need for direct verification. But the tone had shifted fundamentally. Scientists weren't dismissing the biological hypothesis anymore. They were treating it as a genuine possibility that required serious consideration. The press conference lasted 90 minutes. By the time it concluded, the world had fundamentally changed. For the first time in human history, the scientific establishment was publicly acknowledging that life beyond Earth might not just be possible in theory, but present in reality, traveling through our solar system aboard an ancient comet from another star. And in 4 days, humanity would launch a mission to meet it. The revelation sent shockwaves through every aspect of human society. Within hours of the press conference, stock markets reacted with volatility nobody had predicted. Biotechnology companies surged as investors imagined applications of alien biochemistry. Space industry stocks climbed on expectations of increased funding. Traditional industries fluctuated wildly as traders struggled to price, in a future where humanity was no longer alone in the universe. Religious leaders faced questions they had debated theoretically for centuries, but never expected to confront in practice. Does extraterrestrial life have souls? Does the existence of biology on a comet change fundamental theological principles? The responses varied dramatically across faiths and traditions. Some religious authorities embraced the discovery as evidence of creation's vastness and diversity. Others called for caution, warning against premature conclusions. A few rejected the findings entirely, insisting they were either misinterpretations or deliberate deceptions. The United Nations convened an emergency session of the Committee on the Peaceful Uses of Outer Space on May 2nd, 2026. Delegates from 60 nations gathered to discuss protocols for potential contact with extraterrestrial biology. The 1967 Outer Space Treaty had provisions about planetary protection, preventing contamination of Earth with alien organisms. But those provisions assumed human missions bringing back samples. Nobody had written rules for what to do when alien life arrived on its own aboard an interstellar comet. Philosophical implications dominated academic discussions and late-night conversations alike. If life could arise independently in at least 2 locations, Earth and whatever system spawned 3I Atlas, then the universe might be teeming with biology. The Fermi paradox, the question of why we haven't detected alien civilizations if they're common, took on new dimensions. Maybe life was everywhere, but intelligence was rare. Maybe the galaxy was full of microbial ecosystems on comets and planets, but consciousness remained exceptional. Public reaction split along predictable and surprising lines. Science enthusiasts celebrated the confirmation of what many had always believed, that life must exist beyond Earth, given the universe's vastness. Skeptics questioned whether the evidence truly supported the biological interpretation, or whether scientists were seeing what they wanted to see. Conspiracy theorists wove elaborate narratives about government cover-ups and hidden knowledge finally being revealed. Social media became a battleground of opinions, memes, and misinformation. Videos explaining the science accumulated millions of views. Speculation about what the organisms might look like spawned countless artistic interpretations. Arguments erupted over whether humanity should be drilling into the comet at all, or leaving it undisturbed. Some voices celebrated humanity's drive to investigate and understand. Others warned that disturbing alien biology could have unforeseen consequences. But beneath all the debate and speculation ran a current of something deeper. Wonder mixed with unease. Excitement tinged with fear. For thousands of years, humans had looked at the stars and wondered if something looked back. Now, potentially, the answer was yes. And that answer changed everything about humanity's place in the cosmos. even before anyone knew exactly what form that something took. As the world processed the implications of possible life inside 3I Atlas, a subset of researchers began noticing something that had been overlooked in the initial excitement. The thermal pulses weren't completely regular. There were variations, subtle deviations from the baseline, 0.8 Hertz rhythm that appeared to follow patterns. And patterns, some argued, might be more than just biology. They might be communication. The observation started with a radio astronomer reviewing the thermal data out of professional curiosity. Radio astronomers spend their careers searching for patterns in noise, looking for signals buried in cosmic static. When that same pattern-seeking mindset was applied to the temperature fluctuations from 3I Atlas's chambers, something emerged. The pulse intensity varied over longer timescales. Sometimes the thermal spikes reached their normal peak. Other times they climbed higher or fell short. And when those variations were plotted over days and weeks, they didn't look random. The sequence appeared approximately every 48 hours. A strong pulse followed by 2 weaker ones, then 3 strong pulses, then 5, then 8. It took several repetitions before anyone recognized what they were seeing. The Fibonacci sequence, each number the sum of the 2 preceding ones. 1, 1, 2, 3, 5, 8, 13. It's a mathematical pattern that appears throughout nature in spiral shells, flower petals, branching plants. But finding it encoded in thermal pulses from a comet raised questions that went beyond natural phenomena. Other researchers found different patterns. When temperature data was converted to binary, designating strong pulses as 1s and weak pulses as 0s, sequences emerged that some interpreted as prime numbers: 2, 3, 5, 7, 11, 13. Primes are integers divisible only by themselves and 1. They're fundamental to mathematics, and many scientists have proposed using them as a universal language for communicating with extraterrestrial intelligence, because any technological civilization should recognize their special properties. The SETI Institute, the organization dedicated to searching for signals from alien civilizations, activated protocols that had been theoretical for decades. If 3I Atlas was transmitting information, even unintentionally, standard contact procedures needed to be followed. Don't respond until intentions are understood. Document everything. Look for additional signals. Prepare for the possibility that what appeared to be simple biology was actually something far more complex. Skeptics argued forcefully against the communication interpretation. Humans are pattern-seeking creatures. We see faces in clouds, hear messages in static, find meaning in randomness. The thermal variations could easily be artifacts of measurement uncertainty or natural fluctuations in metabolic activity. Claiming they encoded mathematical sequences required extraordinary evidence, and a few apparent number patterns didn't meet that standard. The probability of finding some mathematical sequence in any sufficiently large dataset was actually quite high if you looked hard enough and weren't too strict about what counted as a match. But defenders of the Huizi-Anqiu communication hypothesis pointed out that biology and mathematics aren't mutually exclusive. Even terrestrial organisms show mathematical patterns in their structure and behavior. Heartbeats have natural variability that can appear patterned. Circadian rhythms follow complex cycles. If something inside 3I Atlas was using metabolic cycles that happened to align with mathematical sequences, that could be adaptation rather than message. Perhaps using Fibonacci-based timing optimizes energy distribution in whatever biochemistry was operating inside those chambers. The debate remained unresolved as the launch date approached, whether the pulses represented deliberate communication, biological coincidence, or human pattern recognition run amok. They added another layer of mystery to an already inexplicable situation. The only way to know for certain was to reach the comet, to sample the chambers directly, to see what was generating those rhythms. And on May 4th, 2026, humanity would take the first step toward that answer when the Atlas bioprobe lifted off from Kennedy Space Center, carrying instruments designed to decode whatever secrets lay hidden beneath 400 meters of ancient ice. While most of the world focused on the wonder of potential alien life, a smaller group of scientists was asking a darker question. What if 3 I-Atlas represented not just a discovery, but a threat? What if bringing extraterrestrial biology into contact with Earth's biosphere was one of the greatest risks humanity had ever taken? The concern wasn't science fiction paranoia. It was grounded in solid biological principles. Earth's organisms evolved together over billions of years, developing immune systems and competitive strategies shaped by constant exposure to each other. Bacteria fight bacteria. Viruses infect cells that have defenses against viral infection. The entire ecosystem exists in a dynamic balance where every organism has encountered similar challenges and developed responses. But biology from another star system would have evolved under completely different conditions. It would use different biochemistry, different metabolic pathways, potentially different genetic mechanisms. Earth's immune systems wouldn't recognize it. Our cells wouldn't know how to defend against it. And if that alien biology happened to find Earth's environment hospitable, if it could metabolize our organic molecules and reproduce in our conditions, it could spread without any natural checks on its growth. The scenario had precedent in terrestrial history. When species are introduced to new environments, where they have no natural predators or competitors, they often explode in population. Invasive species devastate native ecosystems precisely because the local biology has no evolutionary experience dealing with them. Kudzu vines smothering forests in the American South, cane toads overrunning Australia, zebra mussels clogging waterways across North America. All examples of what happens when biology encounters an environment unprepared for it. 3. I-Atlas made the situation more complex because fragments of the comet were constantly breaking off as it approached the Sun. Each time it released gas and dust, small particles entered space. Some would be captured by Earth's gravity eventually. Microscopic grains, carrying whatever organisms lived inside those thermal chambers, could drift through the upper atmosphere and settle onto the surface. The contamination might already be happening, invisible and unstoppable. Planetary protection protocols existed specifically to prevent this kind of scenario, but they were designed for human missions. Spacecraft sent to Mars or Europa are sterilized to avoid contaminating those worlds with Earth microbes. Sample return missions use sealed containers and quarantine procedures to prevent any extraterrestrial material from escaping into the environment. But nobody had written protocols for an interstellar comet arriving on its own schedule, beyond human control, shedding material that could land anywhere. Some scientists called for extreme measures. Proposals circulated, suggesting that the intercept probe should be used not to sample the comet, but to destroy it. A well-placed explosive could fragment 3 I-Atlas into pieces small enough to burn up completely in Earth's atmosphere if they ever approached. Others argued for deflection, using the probe to alter the comet's trajectory and ensure it never came close enough to Earth for material transfer to be a serious risk. These suggestions faced immediate pushback. Destroying what might be the first confirmed extraterrestrial life humanity had encountered was unthinkable from a scientific and ethical standpoint. The knowledge contained in those chambers could be invaluable. Understanding alien biochemistry might revolutionize medicine, agriculture, materials science. And there was a deeper principle at stake. If life was common in the galaxy, if organisms routinely traveled between star systems on comets, then Earth had already been exposed to extraterrestrial biology countless times over its history. The late heavy bombardment 4 billion years ago had pelted the planet with millions of comets. If any of them carried life, the contamination happened long ago. But that argument provided cold comfort. Just because Earth might have survived previous exposures didn't guarantee safety from 3I Atlas. Evolution is unpredictable. Maybe previous comet organisms couldn't survive Earth conditions. Maybe this one could. Maybe the dice had been rolled millions of times and Earth got lucky. Maybe this time the luck would run out. The intercept mission was proceeding regardless. But alongside the excitement and wonder, a thread of genuine fear ran through the scientific community. Fear that humanity was about to open a door that could never be closed. While most of the world focused on the wonder of potential alien life, a smaller group of scientists was asking a darker question. What if 3I Atlas represented not just a discovery, but a threat? What if bringing extraterrestrial biology into contact with Earth's biosphere was one of the greatest risks humanity had ever taken? The concern wasn't science fiction paranoia. It was grounded in solid biological principles. Earth's organisms evolved together over billions of years, developing immune systems and competitive strategies shaped by constant exposure to each other. Bacteria fight bacteria. Viruses infect cells that have defenses against viral infection. The entire ecosystem exists in a dynamic balance where every organism has encountered similar challenges and developed responses. But biology from another star system would have evolved under completely different conditions. It would use different biochemistry, different metabolic pathways, potentially different genetic mechanisms. Earth's immune systems wouldn't recognize it. Our cells wouldn't know how to defend against it. And if that alien biology happened to find Earth's environment hospitable, if it could metabolize our organic molecules and reproduce in our conditions, it could spread without any natural checks on its growth. The scenario had precedent in terrestrial history. When species are introduced to new environments where they have no natural predators or competitors, they often explode in population. Invasive species devastate native ecosystems precisely because the local biology has no evolutionary experience dealing with them. Kudzu vines smothering forests in the American South, cane toads overrunning Australia, zebra mussels clogging waterways across North America. All examples of what happens when biology encounters an environment unprepared for it. 3I Atlas made the situation more complex because fragments of the comet were constantly breaking off as it approached the sun. Each time it released gas and dust, small particles entered space. Some would be captured by Earth's gravity eventually. Microscopic grains, carrying whatever organisms lived inside those thermal chambers, could drift through the upper atmosphere and settle onto the surface. The contamination might already be happening, invisible and unstoppable. Planetary protection protocols existed specifically to prevent this kind of scenario, but they were designed for human missions. Spacecraft sent to Mars or Europa are sterilized to avoid contaminating those worlds with Earth microbes. Sample return missions use sealed containers and quarantine procedures to prevent any extraterrestrial material from escaping into the environment. But nobody had written protocols for an interstellar comet arriving on its own schedule, beyond human control, shedding material that could land anywhere. Some scientists called for extreme measures. Proposals circulated suggesting that the intercept probe should be used not to sample the comet, but to destroy it. A well-placed explosive could. Fragment 3, I-Atlas into pieces small enough to burn up completely in Earth's atmosphere if they ever approached. Others argued for deflection, using the probe to alter the comet's trajectory and ensure it never came close enough to Earth for material transfer to be a serious risk. These suggestions faced immediate pushback. Destroying what might be the first confirmed extraterrestrial life humanity had encountered was unthinkable from a scientific and ethical standpoint. The knowledge contained in those chambers could be invaluable. Understanding alien biochemistry might revolutionize medicine, agriculture, materials science. And there was a deeper principle at stake. If life was common in the galaxy, if organisms routinely traveled between star systems on comets, then Earth had already been exposed to extraterrestrial biology countless times over its history. The late heavy bombardment 4 billion years ago had pelted the planet with millions of comets. If any of them carried life, the contamination happened long ago. But that argument provided cold comfort. Just because Earth might have survived previous exposures didn't guarantee safety from 3 I-Atlas. Evolution is unpredictable. Maybe previous comet organisms couldn't survive Earth conditions. Maybe this one could. Maybe the dice had been rolled millions of times, and Earth got lucky. Maybe this time the luck would run out. The intercept mission was proceeding regardless, but alongside the excitement and wonder, a thread of genuine fear ran through the scientific community. Fear that humanity was about to open a door that could never be closed. In the final days before launch, as engineers prepared the Atlas bioprobe for its journey, astronomers continued intensive observations of 3 I-Atlas. Each new spectroscopic session revealed additional details that made the biological interpretation harder to dismiss. The molecular evidence wasn't just consistent with life anymore. It was becoming overwhelming. The breakthrough came from the James Webb Space Telescope on May 2nd, 2026. Webb's infrared capabilities allowed it to detect molecules that other instruments couldn't resolve. In the spectrum of gas streaming from 3 I-Atlas, Webb identified adenosine triphosphate, or at least something remarkably similar. On Earth, ATP is the universal energy currency of life. Every living cell uses it to store and transfer energy. When cells need power, they break down ATP. When they have excess energy, they build ATP. It's as fundamental to biology as water. The molecule detected in 3 I-Atlas's emissions wasn't identical to Earth's ATP. The spectral signature was shifted slightly, suggesting a different molecular structure, or perhaps different isotopic composition. But the core components were there. A nucleotide base similar to adenine, a sugar ring, a chain of phosphate groups. Whatever was inside that comet was using molecular machinery recognizable as energy metabolism. The discovery sent waves through the biochemistry community. ATP isn't a simple molecule. It doesn't form spontaneously in nature through random chemistry. On Earth, cells synthesize it using complex enzymatic pathways that require dozens of proteins working in coordinated sequences. Finding it in a comet's emissions meant something inside was actively producing it, maintaining the chemical machinery necessary for its synthesis. Then came the lipid analysis. High-resolution spectroscopy revealed not just phospholipids, but specific varieties that form membranes. On Earth, cell membranes are made of phospholipid bilayers, 2 layers of molecules arranged with their water-loving heads pointing outward and their water-repelling tails pointing inward. This structure creates a barrier that separates inside from outside, allowing cells to maintain different chemical environments. The phospholipids detected in 3 iAtlas showed the same basic architecture, suggesting they could form similar structures. Isotopic ratios provided another critical piece of evidence. Different isotopes of carbon, nitrogen, and oxygen have slightly different masses, and biological processes preferentially use lighter isotopes because they're easier to incorporate into molecules. This creates characteristic isotopic signatures in organic material produced by living things. When astronomers measured the isotopic composition of molecules from 3 iAtlas, they found exactly this pattern. Carbon-12 was enriched relative to carbon-13. Nitrogen-14 was more abundant than nitrogen-15. The ratios weren't identical to Earth's biology. The differences suggested alternative metabolic pathways, but the direction of the bias was the same. Even the skeptics were running out of alternative explanations. Individually, each biosignature could potentially be explained through exotic chemistry, but together they formed a picture that was harder and harder to attribute to non-biological processes. You had membrane-forming lipids. You had energy metabolism molecules. You had amino acids with preferential chirality. You had isotopic signatures, characteristic of biological fractionation. You had organized structures generating heat and pulsing rhythmically. You had increasing activity correlated with increasing energy availability. The statistical argument became compelling. What was the probability that all these features would appear together through purely chemical processes? Each additional biosignature multiplied the improbability. It was like finding footprints, hair, DNA, and video footage of a creature, and still insisting no creature existed. At some point, the simplest explanation was also the correct one. By May 3rd, the day before launch, a survey of astrobiologists found that 78% now believed 3 iAtlas contained biological activity. That was a dramatic shift from early April, when most scientists favored exotic chemistry explanations. The holdouts weren't being stubborn. They were maintaining appropriate scientific caution in the face of an extraordinary claim. But the momentum had clearly swung toward accepting that something alive was riding inside that comet. The molecular evidence had done what telescopic observations alone couldn't. It had provided chemical proof of processes that on Earth only occur in living systems. And if those same processes were happening inside 3 iAtlas, then the most likely explanation wasn't that chemistry had coincidentally recreated every signature of life through different mechanisms. The most likely explanation was that chemistry had done what it apparently does when conditions allow. It had organized itself into something that could maintain itself, extract energy from its environment, and persist across billions of years and trillions of kilometers. It had created life, and in less than 24 hours, a spacecraft would begin its journey to meet that life face to face, to drill through ancient ice and see what form biology takes when it evolves under an alien star. May 4th, 2026, Kennedy Space Center. The sun rose over Launch Complex 39, just as it had for countless missions before. But nothing about this launch felt routine. The Atlas bioprobe sat atop a Falcon Heavy rocket, its payload shroud containing instruments that might, within 8 weeks, confirm the existence of extraterrestrial life. 500,000 people lined the beaches and causeways around the Space Center. Millions more watched via live stream from every continent. Humanity was about to reach out and touch something that had crossed the vast emptiness between stars. The countdown proceeded with mechanical precision through the final hours. Fueling operations completed without incident. Weather conditions remained within acceptable parameters. Systems checks came back green across the board. At T-10 minutes, the launch director polled the control teams. Each station reported ready. The mission that had been impossible 2 weeks ago was actually happening. The final seconds ticked down. At T-0, the Falcon Heavy's 27 engines ignited simultaneously, producing over 5 million pounds of thrust. For a moment, the rocket remained anchored to the pad, while computers verified that all systems were performing correctly. Then, the hold-down clamps released, and the massive vehicle began rising, slowly at first, then accelerating rapidly as it climbed into the morning sky. The roar reached the spectators seconds after the rocket lifted off, a physical wave of sound that rattled windows and pressed against bodies. The Falcon Heavy climbed on a pillar of fire, its engines burning kerosene and liquid oxygen at a rate of several tons per second. At 2 minutes and 30 seconds into flight, the side boosters separated, tumbling away to begin their own return to landing zones on the ground. The center core continued burning, pushing the upper stage and its precious cargo toward orbital velocity. 8 minutes after liftoff, the center core shut down and separated. The second stage engine ignited, burning with a blue flame visible against the darkness of space as the rocket climbed above the atmosphere. 12 minutes into the mission, the payload fairing split and fell away, exposing the Atlas bioprobe to the vacuum of space for the first time. Solar panels unfolded, navigation systems activated. Telemetry streamed back to Earth, confirming that the spacecraft had survived the violent ride to orbit intact and functional. But orbit was just the beginning. The probe remained attached to the Falcon Heavy's second stage for another hour, as both coasted around Earth, positioning for the critical burn that would send the spacecraft on its way to Venus. At 1 hour and 23 minutes after launch, the second stage engine reignited for a 6-minute burn that added the velocity needed to escape Earth's gravity and enter an interplanetary trajectory. When the burn completed, small explosive charges fired, separating the Atlas bioprobe from the rocket stage. The spacecraft was on its own now, a tiny robotic explorer carrying humanity's hopes and instruments on a journey that would cover 200 million kilometers. Over the following hours and days, mission controllers tested every system. The cameras captured test images of Earth receding behind. The spectrometers were calibrated against known stellar sources. The thermal drill ran through checkout procedures, confirming that its heating elements and mechanical systems functioned correctly. The sample collection mechanisms cycled through their operating sequences. Everything worked. Nothing had broken during launch or deployment. The Venus flyby was scheduled for June 8th, 35 days away. During that time, the spacecraft would cruise through interplanetary space, its trajectory carefully calculated to bring it to exactly the right position and velocity when it encountered Venus's gravity well. Controllers would use the time to continue testing systems, to practice operational procedures, and to refine the approach plan based on updated observations of 3I Atlas. The comet was still 2 months away from the probe, but it was already much closer to Earth than when the mission began. Ground-based telescopes tracked it nightly. Its coma continued expanding. Its activity continued increasing. The thermal chambers deep in its interior pulsed with their characteristic rhythm, now approaching 1.5 Hz, faster than ever before. Whatever was inside was approaching peak activity as it drew closer to perihelion. And the Atlas bioprobe was racing to meet it, carrying instruments that would finally, definitively, answer the question that had consumed humanity for months. Was something alive in there? And if so, what was it? May 4th, 2026. Kennedy Space Center. The sun rose over Launch Complex 39, just as it had for countless missions before. But nothing about this launch felt routine. The Atlas bioprobe sat atop a Falcon Heavy rocket, its payload shroud containing instruments that might, within 8 weeks, confirm the existence of extraterrestrial life. 500,000 people lined the beaches and causeways around the Space Center. Millions more watched via livestream from every continent. Humanity was about to reach out and touch something that had crossed the vast emptiness between stars. The countdown proceeded with mechanical precision through the final hours. Fueling operations completed without incident. Weather conditions remained within acceptable parameters. Systems checks came back green across the board. At T-10 minutes, the launch director polled the control teams. Each station reported ready. The mission that had been impossible 2 weeks ago was actually happening. The final seconds ticked down. At T-0, the Falcon Heavy's 27 engines ignited simultaneously, producing over 5 million pounds of thrust. For a moment, the rocket remained anchored to the pad, while computers verified that all systems were performing correctly. Then, the hold-down clamps released, and the massive vehicle began rising, slowly at first, then accelerating rapidly as it climbed into the morning sky. The roar reached the spectators seconds after the rocket lifted off, a physical wave of sound that rattled windows and pressed against bodies. The Falcon Heavy climbed on a pillar of fire, its engines burning kerosene and liquid oxygen at a rate of several tons per second. At 2 minutes and 30 seconds into flight, the side boosters separated, tumbling away to begin their own return to landing zones on the ground. The center core continued burning, pushing the upper stage and its precious cargo toward orbital velocity. 8 minutes after liftoff, the center core shut down and separated. The second stage engine ignited, burning with a blue flame visible against the darkness of space as the rocket climbed above the atmosphere. 12 minutes into the mission, the payload fairing split and fell away, exposing the Atlas bioprobe to the vacuum of space for the first time. Solar panels unfolded, navigation systems activated, telemetry streamed back to Earth, confirming that the spacecraft had survived the violent ride to orbit intact and functional. But orbit was just the beginning. The probe remained attached to the Falcon Heavy's second stage for another hour as both coasted around Earth, positioning for the critical burn that would send the spacecraft on its way to Venus. At 1 hour and 23 minutes after launch, the second stage engine reignited for a 6-minute burn that added the velocity needed to escape Earth's gravity and enter an interplanetary trajectory. When the burn completed, small explosive charges fired, separating the Atlas bioprobe from the rocket stage. The spacecraft was on its own now, a tiny, robotic explorer carrying humanity's hopes and instruments on a journey that would cover 200 million kilometers. Over the following hours and days, mission controllers tested every system. The cameras captured test images of Earth receding behind. The spectrometers were calibrated against known stellar sources. The thermal drill ran through checkout procedures, confirming that its heating elements and mechanical systems functioned correctly. The sample collection mechanisms cycled through their operating sequences. Everything worked. Nothing had broken during launch or deployment. The Venus flyby was scheduled for June 8th, 35 days away. During that time, the spacecraft would cruise through interplanetary space, its trajectory carefully calculated to bring it to exactly the right position and velocity when it encountered Venus's gravity well. Controllers would use the time to continue testing systems, to practice operational procedures, and to refine the approach plan based on updated observations of 3 Aihui Atlas. The comet was still 2 months away from the probe, but it was already much closer to Earth than when the mission began. Ground-based telescopes tracked it nightly. Its coma continued expanding. Its activity continued increasing. The thermal chambers deep in its interior pulsed with their characteristic rhythm, now approaching 1.5 Hz, faster than ever before. Whatever was inside was approaching peak activity as it drew closer to perihelion. And the Atlas bioprobe was racing to meet it, carrying instruments that would finally, definitively, answer the question that had consumed humanity for months. Was something alive in there? And if so, what was it? The Atlas bioprobe reached Venus on June 8th, 2026, 35 days after launch. The spacecraft approached the planet from the sunward side, diving toward the dense atmosphere at precisely calculated angle and velocity. Venus appeared in the navigation cameras as a brilliant crescent, its thick clouds reflecting sunlight with an intensity that required filters to prevent sensor damage. The planet's gravity reached out across hundreds of thousands of kilometers, beginning to bend the probe's trajectory even before closest approach. The flyby maneuver required no engine burns. Gravity would do all the work if the approach geometry was correct. Mission controllers on Earth could only watch as telemetry streamed back, confirming that the spacecraft was following its predicted path with remarkable precision. At closest approach, the probe skimmed just 6,400 kilometers above Venus's cloud tops, close enough that the planet filled the entire field of view of the cameras. For 17 minutes, the spacecraft was on the far side of Venus from Earth, its radio signals blocked by the planet's bulk. During that communications blackout, controllers could only wait and hope that everything was proceeding as planned. When the signal reappeared, telemetry showed exactly what they needed to see. The flyby had worked perfectly. Venus's gravity had accelerated the spacecraft and changed its direction by precisely the required amount. The probe was now on an intercept trajectory with 3I Atlas. The velocity increase was dramatic, over 11 kilometers per second, added to the spacecraft's speed relative to the Sun. That acceleration would have required enormous amounts of rocket fuel if done by engines. Venus provided it for free through gravitational assist. The spacecraft's new path would bring it to the comet on June 27th, 19 days away. During that time, controllers ran continuous tracking to ensure the trajectory remained accurate. Small trajectory correction burns were planned if needed, tiny adjustments to compensate for navigation uncertainties or unexpected forces. But the path looked good. The probe was aimed directly at where 3I Atlas would be, accounting for both objects' motion through space. 3I Atlas was now visible to the spacecraft's cameras, still just a tiny dot against the star field, but growing slowly larger with each passing day. Ground-based observations showed the comet's activity continuing to intensify. Its brightness had increased by over 50% since the probe launched. The thermal chambers were reading nearly 110 degrees Celsius. The spectroscopic signatures of organic molecules were stronger than ever. Whatever was inside was responding to the increasing solar energy, preparing for perihelion, for the moment of maximum heat and light when metabolic processes could run at their peak, and the Atlas bioprobe was racing to arrive just in time to witness it. June 27th, 2026. The Atlas bioprobe reached 3I Atlas after 84 days of flight, covering over 200 million kilometers. The final approach sequence began at a distance of 100,000 kilometers when the spacecraft fired its main engines for the last time, bleeding off velocity to match the comet's trajectory. The burn lasted 18 minutes and consumed most of the remaining propellant, leaving just enough for minor positioning adjustments. At 10,000 kilometers, the comet dominated the view. Its nucleus appeared as an irregular dark shape, roughly 8 kilometers long, tumbling slowly through space as gas and dust streamed from multiple active regions across its surface. The coma, the cloud of sublimating material, extended in all directions, thickest on the sunward side where solar heating was most intense. Navigation became challenging as the spacecraft entered this particle environment. Small ice grains pelted the probe at relative velocities of meters per second, not fast enough to cause damage, but enough to create uncertainty in position measurements. The landing site had been selected weeks earlier based on thermal mapping and terrain analysis. A relatively smooth area near one of the thermal chamber clusters, chosen to minimize the distance the drill would need to penetrate while avoiding active vents that might destabilize the landing. At 100 meters altitude, the spacecraft deployed its harpoons, spring-loaded spears, designed to anchor it to the surface. They fired simultaneously at 50 meters, shooting downward and burying themselves in the comet's ice and rock. Cables went taut, pulling the probe down toward the surface. Contact occurred at 0.3 meters per second, gentle enough to avoid damage, but firm enough to establish solid connection. The harpoon cables reeled in, drawing the spacecraft tight against the surface. Landing legs compressed slightly, absorbing the minor impact. Telemetry confirmed stable attachment. The Atlas bioprobe was down, secured to a comet that had traveled for billions of years across interstellar space. 4 hours after landing, following systems checks and surface surveys, the thermal drill activated. the device extended from its housing on the underside of the spacecraft and positioned itself perpendicular to the surface. Heating elements came online, glowing red-hot as electric current flowed through them. The drill bit began rotating, grinding against ice as thermal energy melted material ahead of it. Liquid water and dissolved minerals flowed away through channels in the drill shaft, carried to collection chambers where sensors could analyze their chemistry. Progress was steady, 10 meters per hour on average, as the drill chewed through layers of ice and rock, descending into the comet's interior. The target depth was 420 meters, where the nearest thermal chamber resided according to radar mapping. At the current rate, penetration would take 42 hours. The spacecraft had power for 48 hours of intensive operations. The margin was thin, but sufficient if nothing went wrong. And 400 meters below, something was generating heat, pulsing with rhythm, waiting to be discovered. At 382 meters depth, 40 hours after drilling began, the thermal sensors on the Atlas bioprobe detected a sharp temperature increase. The drill was approaching the chamber. Controllers on Earth, watching telemetry arrive with its 8-minute delay, held their collective breath. This was the moment. 4 months of observations, 2 months of mission planning, 84 days of flight, and 40 hours of drilling, all converged on what the next few meters would reveal. At 397 meters, the drill broke through. Resistance dropped suddenly as the bit punched into a void. The chamber was hollow as radar had suggested, a cavity in the ice roughly 30 meters across. Temperature inside measured 114 degrees Celsius, far above the melting point of water ice. The drill retracted slightly, and a camera probe extended through the opening, its lens protected by a sapphire window designed to withstand the heat and pressure. The first images transmitted back to Earth showed something that nobody had quite anticipated. The chamber wasn't empty, and it wasn't filled with simple microbes floating in liquid water. Instead, the walls were covered with structures, intricate branching networks that looked almost crystalline, but moved too slowly and deliberately to be mineral formations. They resembled frost patterns on a winter window, except they grew and shifted while the camera watched, extending delicate filaments across surfaces, connecting to each other in geometric arrangements. The structures were translucent, allowing light from the camera's illumination system to pass through them with a faint green tint. That green suggested the presence of the nickel-based chlorophyll analog that spectroscopy had detected from Earth. These things, whatever they were photosynthesizing. They were capturing the faint light that penetrated hundreds of meters of ice and converting it to chemical energy. But they weren't cells, at least not cells as Earth biology understands them. There were no distinct membranes separating individuals. The structures appeared to be one continuous network, a single organism, or perhaps a colony so integrated that the distinction between individual and collective lost meaning. The filaments branched and merged, creating patterns that shifted slowly, reorganizing themselves in response to stimuli that weren't immediately apparent. Spectroscopic analysis of the material showed complex organic chemistry. Carbon-based molecules, certainly, but organized in ways that terrestrial biochemistry doesn't produce. The phospholipids were there, but arranged in layered structures rather than cellular membranes. The amino acids formed chains, but not the proteins that Earth life uses. This was biology, genuine living chemistry, maintaining itself through energy metabolism and organized structure. But it was alien biology operating under principles that evolution on Earth had never explored. The most striking feature was the pulsing. The entire network brightened and dimmed rhythmically, synchronized across the chamber. 1.5 Hz now, faster than the 0.8 Hz observed months earlier when the comet was more distant from the Sun. The brightness changes corresponded to temperature fluctuations, suggesting metabolic cycles where energy was gathered, stored, and released in regular intervals. It looked like breathing. It looked like a heartbeat. It looked alive because it was alive, but alive in a way that stretched the definition of what life could be. The Discovery team struggled for appropriate terminology. Were these organisms? Was this a single organism? Was it a colonial life form, or a biofilm, or something entirely outside Earth's taxonomical categories? The answers would require years of analysis. But one thing was immediately clear. Humanity was no longer alone in the universe. Life existed beyond Earth, not as speculation or statistical probability, but as observable fact recorded by cameras 400 meters inside an interstellar comet. And this life, this strange crystalline network pulsing with ancient rhythms, had survived a journey across billions of years and trillions of kilometers, carried through the cosmic void inside a frozen arc that was older than Earth itself. As the Atlas Bioprobe's instruments analyzed the crystalline networks inside 3I Atlas, a pattern emerged that transformed the discovery from remarkable to revolutionary. The structures weren't just alive. They were organized in ways that suggested purpose beyond simple survival. The arrangement of filaments, the branching patterns, the connections between nodes, all of it followed mathematical principles that appeared too precise to be accidental. High-resolution imaging revealed that the network's geometry repeated at multiple scales. Zoom in on a small section and you'd see branching patterns. Zoom out to view the entire chamber, and those same patterns appeared at larger scales. This fractal organization was efficient, maximizing surface area for energy collection, while minimizing the material needed for construction. But it was more than efficient. It was information-rich. The breakthrough came when a mathematician consulting on the mission recognized something in the branching angles. The filaments didn't extend randomly. They grew at specific angles relative to each other: 60 degrees, 108 degrees, 144 degrees. Numbers from the Fibonacci sequence again, but this time encoded in physical structure rather than temporal pulses. The golden ratio, approximately 1.618, appeared repeatedly in the proportions between different structural elements. Then, the team noticed the nodes, points where multiple filaments connected. These junctions weren't uniform. Some had 3 connections, others had 5, 7, 11, 13 prime numbers, and the distribution of these prime-numbered nodes across the network wasn't random. They formed patterns, clusters, that when mapped created shapes recognizable as geometric forms: triangles, pentagons, heptagons. This wasn't biology simply following efficient design principles. This was information storage. The structure itself was a message, or more accurately, a blueprint. When researchers treated the network as a 3-dimensional code, with different junction types representing different values, and the connections representing relationships, they could extract sequences. Those sequences, when analysed, showed properties consistent with genetic information or instructions for molecular assembly. The implications were staggering. The organism inside 3I Atlas wasn't just alive in the sense of metabolism and growth. It was a self-replicating information storage system. The crystalline networks encoded instructions for their own construction. Given the right chemical, environment, and energy source, these structures could build copies of themselves, propagating not just through cellular division, but through directed assembly of molecular components following a stored template. This solved the interstellar survival problem. DNA degrades over millions of years under cosmic radiation. Proteins denature. Cellular machinery breaks down. But if the information for rebuilding all of those systems was encoded in robust crystalline structures, if the blueprint was written in geometric relationships rather than fragile chemical bonds, it could survive indefinitely. The organism could exist in dormancy as pure structure, then use that structural information to rebuild its metabolic systems when conditions allowed. It was simultaneously more primitive and more sophisticated than Earth life. More primitive because it didn't have the elaborate cellular machinery that terrestrial organisms use. More sophisticated because it had solved the problem of information preservation across cosmic timescales in a way that Earth's biology never needed to develop. This wasn't life as we knew it. This was life designed, either by evolution, operating under conditions we'd never imagined, or possibly by intelligence that understood molecular engineering at a fundamental level. The networks inside 3I Atlas were more than survivors of an interstellar journey. They were messages in themselves, mathematical poems written in crystalline filaments, carrying information across the galaxy in structures that could rebuild, replicate, and spread whenever they encountered suitable environments. They were seeds designed to grow, encoding not just their own reconstruction, but potentially vast amounts of additional information about where they came from, what conditions created them, what purposes they might serve. And humanity had just learned to read the first few words of what might be the most important text ever discovered, written in an alien language of angles and connections, waiting 400 meters inside a comet for someone to finally understand what it was trying to say. The discovery inside 3I Atlas changed everything about humanity's understanding of its place in the cosmos. But the implications took time to fully comprehend. In the days following the probe's successful sampling, as scientists worked to decode the information stored in those crystalline networks, the world grappled with what it meant to know for certain that life existed beyond Earth. The most immediate conclusion was humbling. Life wasn't special to our planet. The chemistry that organized itself into self-replicating, energy-harvesting systems could happen elsewhere, under different conditions, using different molecular strategies. Earth wasn't unique. Biology wasn't a cosmic accident that occurred once in the universe's history. It was apparently something that chemistry does when conditions allow, a natural outcome of physical laws operating on complex molecules. But the 3I Atlas organism suggested something even more profound. Life doesn't just emerge locally, it spreads. Those crystalline networks had survived an interstellar journey that might have lasted billions of years, protected inside their frozen arc, waiting for warmth and energy to trigger their revival. If one comet could carry life across the galaxy, then millions could, trillions could. the galaxy might be thoroughly seeded with biology, with organisms drifting between stars on cosmic timescales, establishing themselves wherever they found suitable worlds. This raised questions about Earth's own origins. Did life emerge here independently, or did it arrive on ancient comets during the late heavy bombardment? The three I-Atlas networks use different biochemistry than terrestrial organisms, suggesting independent origin, but that didn't prove Earth's biology was entirely homegrown. Maybe life on Earth started with simple molecules delivered by comets and evolved from there. Maybe our distant ancestors rode similar frozen vessels from dying worlds or disrupted planetary systems, carrying the seeds of everything that would eventually become forests and oceans and human beings. The discovery also transformed the search for life elsewhere. Scientists no longer needed to focus exclusively on planets in habitable zones around stars. Life could exist in comet interiors throughout the galaxy, in environments that seemed impossibly cold and dark and isolated, but that provided everything that certain forms of biology needed. Comets were common. If comets could host life, then the universe was far more alive than anyone had imagined. The mathematical encoding raised the most provocative questions. Was the geometric information in those networks purely evolutionary, the result of selection pressure favoring structures that could preserve and transmit information efficiently? Or was their design involved? The precision seemed almost too perfect, the mathematical relationships too deliberate. Some researchers argued this was evidence of directed panspermia, of advanced civilizations deliberately creating organisms optimized for interstellar transfer and seeding them throughout the galaxy. Others insisted that evolution alone could produce such sophistication, given enough time and the right selective pressures. Either answer was extraordinary. If evolution alone created the three I-Atlas networks, then biology was even more capable of innovation than Earth's history suggested. If intelligence designed them, then technological civilizations existed somewhere in the galaxy, with capabilities far beyond current human understanding. Both possibilities meant the universe was stranger and more wondrous than the cosmos humanity had inhabited before June 27th, 2026. 3 I-Atlas continued its journey outward from the Sun, carrying its crystalline passengers back into the darkness from which they came. The probe had sampled only one chamber. 6 others remained unexplored, potentially containing variations or additional information. The comet would eventually leave the solar system entirely, becoming once again an interstellar wanderer. But it had accomplished something extraordinary. It had proven that life finds ways to persist across impossible distances and unimaginable timescales. It had shown that biology is a cosmic phenomenon, not a terrestrial curiosity. And most importantly, it had answered the ancient question. We are not alone. We never were. The galaxy has been alive for billions of years, and it's been talking through mathematics written in crystal, through chemistry encoded in ice, through organisms that learned to sleep through the darkness between stars and wake when light returns. 3 I-Atlas was the first message humanity learned to read. But looking up at the night sky, knowing what we now knew, one thing became certain: it won't be the last.